are moving?
Yeah, moving, ma'am. No issues. We can
Fine,
start
fine.
now. Yeah, yeah.
Yeah.
And yeah, hello, one and all. Good afternoon, Eva. Good afternoon to one and all. For our last session of our workshop is going to begin, and we have our guest as a resource person, Dr. Sowmya V from Amrita School of AI, Amrita Vidyapeetham. So I will brief her biography once. Dr. Sowmya V completed PhD in Artificial Intelligence for Natural Scene Analysis from Amrita Vishwa. Her broad research area is AI for signal and image analysis. The sub areas of her research interest include biomedical, agriculture, ecology, and underwater acoustics. She published papers in IEEE Transactions, Artificial Intelligence Review, Multimedia Tools and Applications, Neural Computing and Applications, Computers and Security, Healthcare, Technology, Letters, etc. Her research focus is on explainable AI, discriminative and generative models applied for biomedical data analysis, unmanned aerial vehicles, and satellite image analysis. She received the research seat grant from Amrita Vishwavidyapeetham for UAV image analysis and from Naval Physical Oceanographic Laboratory (NPOL) and Defense Research and Development Organization (DRDO) for the underwater acoustic signal analysis. She has an active research collaboration with Prince Mohammed bin Fahd University, Saudi Arabia, and University of Wyoming. And she is the recipient of several awards such as Women in AI Leadership, NVIDIA Deep Learning Instructor, Young Woman Researcher. She served an invited speaker in adult FDPs conducted by NIT and session chair in various international conferences. Welcome you, ma'am, for this platform of International Workshop of Computation Intelligence 2023. Yeah, platform is yours, ma'am. Thank you. Yeah, please go ahead.
Thank you, Dr. Rahul. Thank you for your kind introduction. And good afternoon to all the participants here. Before starting, I would also like to thank the Chief Patron, Professor Soman, who is the head of artificial intelligence, for a man who is behind the complete training of who am I and what I am today. Thank you. And I'm glad to be the last speaker of this international workshop on computational intelligence. I request the participants to feel free to interrupt whenever you have the queries or you have to open up for any discussions. So I'm open for it. So the topic for today is transformers in computer vision. So to start with, the for the next 1.5 hours, maybe like the last 10 to 15 minutes, we can have it for the interaction. So the flow of the presentation is designed such that we'll see what is transformer, what are the important components of transformer, and I'm pretty sure that all the active participants who have already worked or familiar with your deep learning framework, especially to deal with the images, you would have heard or you would have worked enough algorithms about convolutional neural network. So the question is how this transformer is different from convolutional neural networks, or how the transformer can go in alignment with convolutional neural networks for the better tasks in terms of all the computer vision applications. Okay, so the overview, the to start with, what is transformer? You can see that the key term or the component that is connected with the transformers is, which is termed as self attention. Okay, so this is it. Hope I'm audible, right? Yeah, fine.
Yes, ma'am. Please
So
go ahead.
if you just see that the most important component of the term, which is actually called as the self attention. So if you see this self attention, so how it is actually in contrast to the recurrent neural networks, say RNNs, or the convolution. So what is that is, if you see that the sequence aligned, say for example in RNN, if you go for the text, it takes one word at a time, right? So that you form it as a sequence here. But whereas transformer has a potential to see all the words at a once. And you can to start with the history of the transformer, it was actually a very successful model in natural language processing, which people have it as a BERT, so bidirectional encoder representation from the transformer. So people from the computer vision community community borrowed it from the natural language processing, which is actually other way around. If you see for the convolution neural networks, convolution neural networks emerged with the images. Later, it was actually adopted by the natural language processing community when the algorithm of a word to vec representation came, right? So how a word can be represented as a vector, then they started using the 1D CNN. Okay, so if you see this one interesting or the article which we can look for to know only about this transformers with the attention is that attention is all you need, which was actually published in 2017. So it is also called as the intra attention. So why it is called as the intra attention is within an image, okay, or within a sentence, what is the connection between this? We are able to capture it through this attention mechanism. Okay, so the representation of any sequence of the images or in the sentence, you're going to bring an important component called self attention, or in other means or other terms, it is called as the intra attention. So to move ahead, what is the difference or what is a transformer versus the most known recurrent neural networks? Okay. So in people also call this transformers a non-sequential. So why or what is the important property that is hidden with? We'll see as we move on through the slides. So as I've already mentioned, in your recurrent neural networks, you're going to deal with the sequential data, whereas in transformers it is non-sequential. And let's see that, no, what is this non-sequential mean when you take image as the input. And as I've mentioned, one of the most important components is actually the attention mechanism. So the attention mechanism, I kindly request the participants to mute yourself unless otherwise if you don't have any specific doubts. Fine, thank you. So the transformers use as I've already told, the important component there is actually called as the intra-attention or the self-attention mechanisms. So what is this or what it is helping to understand is the context of the image, which was actually not able to capture or not able to done in case of the convolution neural networks. And it is also able to access the past information. So how are they able to achieve it is a whole lot what are we going to discuss here. And the other important aspect here with respect to the attention mechanism is you can see that there is a specific part which is called as the positional embeddings. And this is one of the important part in the vision transformers, or the transformers that is designed especially for the computer vision applications or with respect to the images. Okay, so you can see that the two parts or the two important components that comes into picture. One is the attention mechanisms or the intra attention, which will deal with the sequence or patches in case of the images. And the second one is the positional embeddings. The positional embeddings is the one which is helping the transformers to store the information. Say, for example, if you go for a sentence, there is actually a sequence that has to be followed by the words in order to have it as a proper sentence, right? So how do you have it in terms of, how do you relate this to the terms of the images, and why do you need that as a positional embeddings? What is the role of it is what we are going to pay the essence for. In addition to this, if you see the transformers, how are they being trained is, it is the it's a kind of a transfer learning. The component which comes in is actually self-supervised. So one of the most important thing which we have to understand in this era. So in the early stages of the deep learning, that may be in the early 2010 or 11, if you look for, people have completely looked for an approach which is called as the supervised approach. So what is the supervised approach? You have the data which is labeled. So you're able to annotate the data so that your CNN or convolutional neural network or the deep learning algorithm is able to learn from the data and was able to perform better. So as the days go by, the annotations or labeling of this data in every domain has become really very hectic, or it has become a humongous task, because you know that it is not possible to label all your data connecting to any domains. Okay. So if, for example, if you want to label it for a biomedical domain, yes, of course, you need the expert of the doctors to be involved to annotate it. but do you expect the doctors to sit to along with you to annotate each and every image? So that is not actually possible, because deep learning requires large amount of data. So in that case, people were moving towards the open research area is towards the self-supervised, semi-supervised, and unsupervised approach. Okay, so if you say unsupervised, it is completely with an unlabeled data. If it is semi-supervised, partly the data is labeled and the rest goes for the rest of it goes for the algorithm to learn and make it as the label. And self-supervised, it is something no learning on its own of about the labeling or about the managing the data. So this aspect is one of the important part in transformers. Let's see that how it is able to achieve. Okay, so the other important aspect which we're going to touch is the self-supervised approach. So once the network has been self-supervised on the large amount of unlabeled data, later that network is actually fine-tuned to a specific task of any classification with a minimal data that has been labeled. So that is one of the great breakthroughs in transformers. But of course, this also demands for the large amount of data, but it is a self-supervised approach. So so far, so what I've touched so far is the different components or the important components in the transformers, which actually makes it different from the convolutional neural networks or the recurrent neural networks. So one of the important aspect is the attention mechanism, and the other one is the positional embeddings, which you also have. The third one is the how do you make it as a self-supervised training and adapt it towards the particular or you narrow down to your specific task. So just moving along. So before continuing, just a second. Uh, yeah. So I'll just turn off my video if it is fine. So if there is any queries or things, please let me know, or you can have it in the chat so that I'll turn on my video to discuss further. Hope, is that fine, Dr. Rahul?
Yes, ma'am. If you can turn
Yeah.
off the video, then could fine, I think so.
Yeah.
There is one question between that. Pooja is asking, what is the difference between self-supervised and reinforcement approaches?
Yeah, so I think I'll address that before moving, as I've already told that participants can interrupt. So just a second. So the question was, what is the difference between the self-supervised and the reinforcement learning? Okay, no, so self-supervised, if you see, it is what they are trying to do is that they are trying to learn it. I'll cover it in detail, but just to touch upon, you can see that there is an approach called contrast learning approach. So what do you mean by contrast learning approach is you want to see, if say, for example, if you want to classify an object, we are expecting the network to learn the significant features that are actually different from the identifying with respect to the other objects. So you're just giving people call this as a positive and the negative sample. So I have the when I come to that particular portion, I'll explain in detail, but just Puja, to be on sync, I'll just have these terms now. So if you go for the reinforcement learning, you are trying to make the network learn by providing the rewards and also the penalty. So you design two different kinds of functions. One is a reward function, other one is actually penalty function. But here you're talking only in terms of the maybe you can call it in terms of no the penalty you can consider, or you can map it towards a loss, and you are trying to minimize the loss by just seeing no the most significant matching features. Okay, so that is the main difference. So Puja, if it is not clear, please let me know so that others may also be benefited of it.
Yeah, and also Remya is asking, is supervised same as of that of active learning? Uh,
It comes under one type of active learning. So semi-supervised, if you see, again, there is okay, the proper term that comes in is actually student-teacher model. Okay, so if you want to, okay, Pooja got it partly. Maybe like, yeah, at the end of the session, you can just get back if still it's not clear. Yes, semi-supervised. Yes, Ramya was asking about semi-supervised approach. Yes, of course, it is one of the active learning approach. So that also I'll have it here as a student teacher model, right? So teacher always has the global perspective of any course, and the student will be able to get the local perspective every time when finishes of the lecture, and we'll see that whether he's able to map it to the global, although he'll not be able to get it on 1 or 2 lectures, right? So similarly, like how Pooja got it now, so whatever I'm telling, it's on my perspective I'm explaining, but Pooja from the listener perspective, she's trying to get thing, but maybe like after 2 hours she may able to get it more better after hearing the complete things, right? So that is where the student teacher model comes into picture, and that is where the semi supervised approach part, and of course it is one of the active learning approach. Yes, hope I've answered it. Fine. I think I can proceed, Dr. Rahul. Yeah.
Yes, ma'am. We
Yeah.
can the last we can take, ma'am.
Yeah,
We
of course,
explain
that'll be
everything.
fine.
Yeah,
Yeah.
yeah.
Okay. So if you see this, I think this is one of the very fine, because your image speaks better than the words. So so acknowledgement to Professor Hinton, who has given such a thing. So he was even giving the same in terms when he was introducing the capsule networks, right? So if you see this, left side is actually the phase, right? The representation for a phase are mainly it is a feature of your eye, nose, and the mouth. Of course, you have the other features, but the most significant features when we recognize a person is mainly their eyes and the other features. So what your CNN captures is that it captures these feature representations independently. Say for example, no, it doesn't learn about the orientation of this, like how the eye should be placed, or how the nose's relative position to the eye or the lips. Okay, so the relative embeddings of these features will be missing in your convolution neural networks. Okay, and if you see this, you need a very large receptive field. What do you mean by a large receptive field? Is that I want to see an image as a whole in order to understand this. But CNN, you know that in order to capture the features in depth from the data, they'll be just capturing it as the small windows. Okay, people call this as capturing the local features as the patches. Okay, so the main limitation, we can't it's really not good to put the word as no disadvantage, but the limitation of the CNN is that it will not be able to, or it has a limitation in encoding the relative position of the different features, whereas for which it requires a large receptive field in order to capture this long range dependencies. But how this attention is able to capture this, and which is actually the limitation of the convolution neural network. So this represents that your convolution neural network it's actually very good, or it's actually best in getting the features, but the orientations of the alignment of the features it will not be able to capture. So before moving to the how this attention works, so this is the taxonomy of the self attention. So all the reference papers from which the figures has been taken has been given at the bottom. The link has been given at the bottom of the slide. So if you see through this, this is one of the very top survey paper, which is the transformers in vision. Okay, so in this part, I didn't cover the which are the survey that has been given under the videos or the 3D analysis, but rest of the things, it is whatever thing which comes under the area of my expertise has been covered. Okay, so if you see this, the self attention in the vision models, the very broad categories under this. One is the single head self attention. The other one is the multi head self attention. Okay, and this multi head self attention plays an important role, or plays an important component in the vision transformers. So under this multi-head self-attention, you have the uniform scale. Just a second. Yeah. So you have the uniform scale, you have the multi-scale, and you have the hybrid. That is the advantage of the transformer and the advantage of the convolution neural network, which has been merged and come out as an hybrid vision transformers. And finally comes the self-supervised vision transformers. So we'll cover the state of the art transformers, or state of the art network models under each of these categories. One in uniform scale, multi-scale, hybrid VIT, and the self-supervised vision transformers. So to proceed ahead, so this is what we are going to cover it for the next 1.5 hours. So to move ahead, what is this single head self attention? So as I've already told, self attention is one of the important component in the transformers. In that, what we have is the single head self attention. So what is the single head self attention is that, so in transformers we have to be familiarize ourselves with three components or the three sub components under the self attention, which is called as the query, key and value. Okay, so that is where Q stands for query, K stands for key and V stands for value. So what is this attention score? Okay, what is this is, that is nothing but the finally what is this attention is nothing but the weighted sum of the values which has been assigned for your value in each of this corresponding key, right? So if you have an image, it will be looking for the query, key and value. So what are you going to do is that, remember that both the each of the query and queue is going to depend upon a weight matrix. So that is what your transformer is going to learn. If you want to map it to the convolution neural networks, it be what we call it as a small receptive field, which is a filter. So the values that is associated with the filter is actually called as a weights, right? So similarly here, and moreover, you can see that in convolution neural networks, all the patches will be shared by the same weights. Okay, but whereas here, in the transformer, the image itself will be divided into multiple patches, and each of this patch will be associated with a query, key and value. So you have the matrix multiplication with a query and key, which you are scaling it and applying a softmax function. So this whole operation forms the attention score for your value. Okay, so this tells that each of the block features how important it is. So how will you know that how important it is? It will be associated with the corresponding attention score. That is what is actually called as the weight of that attention. So I mean weight of that patch. So that is what is termed as the attention score. So finally, the matrix multiplication comes along with the what is been applied with the softmax. So remember that Q is also a matrix, K is also a matrix. So to match with the dimension, you make it as Q, K transpose. And in order to scale it, you have the 1 by square root of dk. And you're applying the softmax function over it, which overall gives you the attention score for all the values that has been captured with the V matrix. So just moving ahead to give it in the detailed form. So this you can see it as the two matrix multiplications. So one matrix is nothing but the softmax of Q can, K transpose over the square root of dk. So this one, if you see, the matrix size is going to be m cross n. So you have the Q matrix of size, say m cross dk, and K can be the size of dk transpose can be the size of dk cross n. So totally the matrix size after this qk transpose by square root of dk softmax, if you take, because softmax is applied over a vector, so the vector contains n elements, so that is how each row has been packed. So this matrix size, the first matrix which I'm talking about, becomes a size of m by n matrix, which will be multiplied with the value matrix of n cross dv. Okay, so the final matrix size becomes m cross dv. So this is just a dimension that has been given. So the main thing what we have to understand is that, so if people, if already you would have went with the linear algebra course, you would have heard called as, no, which is called as a dot product, or in other terms it is called as a fraction, right? So what is this matrix matrix multiplication view we have to do? I think this is covered as part of the by Professor Soman in the first session. So he was telling that the two matrix multiplication can be viewed as one in terms of the dot product, or in other terms you can view it as a linear combination of the columns. So in this case, you have to take it as the view of the dot product. So if you just see this matrix multiplication, how am I going to do is that first row multiplied by the first column, right? So in this first column for V11, I'm going to rely on the value of softmax of E11 by square root of dk. So that becomes my A11, or that is going to be my attention score for the first patch of my first sequence in an image. So that is how you have to make an interpretation for this operation. So what you have is actually a set of attention scores. So those attention scores, so you're going to finally represent it as the weighted sum of the values. So what is that weighted sum? Is nothing but your attention scores. How are we getting it? We are getting it through the query and keys. Okay. So this part is what your transformers is learning, or transformer network is learning, which is actually in contrast with your convolution neural network. So moving ahead, so to just give a broad explanation for it. So how you will you pass your images? You will not just pass your one image as a whole. You will be passing it as the patches. Okay, so your small patches of the images becomes your sequence or the input to your transformer model. So you will be looking for three components: query, key, and value. So each of this will be subjected to a weight matrix, as WK stands for the matrix associated with the key, matrix associated with the query, and the matrix associated with the value. And remember that these weights are actually the it's actually the learnable parameters of the transformer model. So what do you mean by the learnable parameters? It is not been manually defined. So it is actually learned by the model through your different iterations or the epochs, right? So then what is the operation you're doing? So you have your Q. In order to match with the dimension, you make it as the K transpose, and then you apply the softmax. So what you get through this is your attention scores. So it is actually, this is shown in terms of the grayscale representation. So you can see that no, it is varying between 0 to 1. It is scaled so that your attention score, the maximum value will be 1, the minimum value will be 0. So if you want to map it towards a color, zeros, the black corresponds to the value 0, white patch corresponds to the value 1, and the intermediate gray patch corresponds to the value 0.5. Okay, so that is how we visualize. So if you see that the white will be the most attentive patch, and the black will be the least attentive, and gray will be the average attentive. So that is the visual representation what are we getting through. And as we know that the algorithms will be able to understand only the numbers, this is how the weight values are being mapped. Okay, so this is multiplied with your values. Okay, so this serves as your score for each of the value, and finally you're getting your self-attended feature maps. So in the feature maps, you will be able to see which patch of the feature is really very important. And now you can connect the point why the positional embeddings is required, because I must know that the patch should, I should correspond that the patch should lie in the which portion of my image, which can be captured only if you do it with the positional encodings. Say, for example, if I encoded the first 3 by 3, you can see this blue color thing as a 3 by 3. So totally, there are actually 9 patches, right? So I should label as 0, 1, 2. So the 0th patch, if I get, that corresponds to the left corner of the image, and 8th patch corresponds to the right corner of the image. So corresponding attention map, if I could see that the 0th patch is which has the maximum attention score, so I can just go and see that that is the corresponding feature in my image, which has to be, which has the high, which is the most dominant representation of the feature in order to represent that particular object in an image. So that is what the relation actually goes on. Okay, so this one, in order to get it as in terms of the weighted values, is why this activation function, which is one of this, okay, which you call it as a softmax, has been applied here. Okay, so hope this is clear. So this is one of the most important components in the transformer. So the extension of this single head self attention goes as the multi head self attention. So this is easy to understand if we have really understood what is the single head self attention is. So as I've already mentioned, the you can just see in the lower part half of the slide, which is called as the, or which is termed as the scaled dot product attention. Okay, the scaled dot product attention is what is actually called as the single head self attention. So this is termed in terms of the, using the term from the concept of linear algebra. So you have the matrix, the same thing, matrix multiplication over the query and key, which has been scaled and which has been activated through the sigma, or it is called as the softmax. The activation function is represented as sigma here, which is nothing but the softmax. And then you are multiplying that with the corresponding value. So this output serves as your attention score, and that when you multiply the value, you'll be able to see about the self-attended map, which is nothing but your feature map corresponding to your input sequence. So when you have this as a multi-head self-attention, what are we going to do is that you're going to concatenate multiple single heads. Okay. So it is something, no, your attention over attention you're giving, so that you have no head 1 to head h. This head 1 to head h is nothing but your single head self attention. So in convolution neural network, you can see that it is the same convolution operation. As you go deep, your number of filters goes on increase and goes on deep as a number of feature maps increases, right? So similar way, in this you can map that the single head self attention has been concatenated with the multiple times. That is what is actually called as the multi-head. And you have the weight matrix for it, which has been represented as WO here, in order to match it with the dimension of your original input. Then only you can map your feature dimension. Okay. So in this case, if you see the number of multi-heads required is that becomes the hyperparameters, or that becomes one of the parameters to be defined by the user for the transformer model. Okay, so you know that any DL architecture that comes under the AI algorithm, it actually has a set of parameters which are called as, or which are known as hyperparameters. So when we say hyperparameters, those are the parameters which has to be fixed based upon your experimental analysis. Like if you run for, say for example, one of the very base hyperparameter which people would have been heard is the epoch. So number of epochs, how do you fix it? You don't have any precise mathematical proof for, no, this is your fixed number of epochs for this kind of data. Okay, so how do you do? What we do is that we just trap the either loss or the accuracy using your validation data, and see for after what number of epochs this gets saturated, and you fix with your minimum number, because your model, you're going to use your, you're going to deploy a trained model. So how many times you're going to train it depends upon the network parameters. Okay. So in this, the number of multi-head, the number of single heads that actually come under the multi-head becomes the one of the hyperparameters of your transformer network. So how do you define this multi-head? It is nothing but the attention over your ith head. Okay, so this I varies from 1 to h. So 1 to h number of single heads you have, or single self attention you have, those things you're concatenating in order to reach it towards your multi-head attention. Okay, and this forms the important, this multi-head attention forms the important block, or one of the important feature part towards your transformer models. Okay. So moving ahead, one kind of attention, what we will see is actually no channel attention, which is called as the squeeze and excitation. So this one, I'll show it no how one of our BTEX team. Okay, so here I would like to tell you that we run a course on BTEC in artificial intelligence, which is run by the Department of Artificial Intelligence and the School of AI. And here also I must highlight Professor Soman for initiating such a thing in the Board of Studies. So here, if you see that all the courses, they have to do a term project at the end of every course. So this, the BTech students started this work right in their semester 6, when they were doing their deep learning for signal and image processing. So they have a base course of signal and image processing in semester 5. Followed by it, they'll be doing a course on deep learning for signal and image processing. So one of the teams have done this work, and they've continued this as a BTech project. And I'll tell you what is the outcome they have led. Okay. So the one of the attention, channel attention. Okay. So if you just go for this, why we call this as a channel attention is you have the backbone of the CNN coming here, convolution neural network coming here. Okay. So this kind of attention, one kind is actually called as the squeeze and excitation. So this was presented in the IEEE conference on computer vision and pattern recognition. So one of the top rated computer vision conference. This was presented in 2018. So what has been done is that you have a particular feature block when it comes from the convolution neural network. So you have a spatial dimension. So that is what is being represented by height and the width. And the number of feature maps is what is actually called as the channels. Okay. So if you have used 100 filters in the previous layer, you will be getting 100 feature maps. So that is the basic of the convolution neural network. So in order to get the global view, okay, so that is what one kind of thing which is present in the attention framework and which was missing in the convolution framework. So how are they trying to bring this is they call it as a squeeze and excitation. So squeeze means you are trying to get the most dominant features, and when you are exciting it, what you're going to do is that the most dominant features are highlighted. So one, you will have it in your a kind of an encoding side, and the other you have it in the decoding side. So how this has been done is that the squeeze is been done using an operation called global average pooling. So this is one of the well-known operations. So either in all the convolution layers will be followed by a max pooling layer. Okay, and finally you have it as the average pooling layer. So max pooling means you will take the maximum value out of it. But since you are looking for your global aspect for every channel feature map, right? So you have to do an average pooling here. So how will you do an average pooling? You take the spatial height and width of every channel. Okay. So I'll go with an example here. Say suppose my height and width of the channel are 256 cross 256. And like that, say suppose if I have 100 channels. So what should I do? I should take the first 256 cross 256 and I should compute the average of this matrix because my matrix size is 256 plus 256. So what I'll do, I'll just sum all these value, divide by 256 square. That gives me my global average value. So this operation, you have to repeat it for every channel. Okay. So suppose you have used 100 filters. That means you'll be having 100 feature maps. Okay. So that after doing a global average, you will be getting one value for one channel. So totally this becomes, or this feature vector becomes the size 1 cross 1 cross C. So each of the channel will be having a scalar value that is nothing but the average value that represents the that captures the global feature from every channel. This is what is the squeeze block. So what they do in the excitation block is they connect this output to a fully connected layer so that their weight matrix will be learned because you want all the neurons in the global average out as an output of the global average pooling. This goes as an input to your fully connected layer. So this learns the weight matrix that connects all the neurons from the global average pooling to all the neurons in the next layer, next fully connected layer. So you will be able to get a weighted score. Of course, this has also been done, or this has also been applied with a activation function. So you'll be able to get the scores. So this was one kind of operation or one kind of thing that has been done for the channel attention. So what, I mean, if you go in detail, so you have X as a feature map. Remember that to get the X as a feature map, people were using the convolution neural network. One of the, any standard convolution neural network comes as the backbone here. Okay. So the last convolution layer from your already or standard convolution neural network architecture goes as an input here. So this will be subjected to the global average pooling. So out of this, it becomes every spatial map, you'll be getting a corresponding average value. So this will be there for the all the channels. And then the channel reduction is done by connecting it to the fully connected layer. So the C will be reduced by C by R. And you have an activation layer, which well known as the rectified linear unit, because this goes as the max of 0, x. So you don't have any saturating thing as in case of the sigmoid. So it avoids the vanishing gradient problem. Okay. So if those terms are not clear, we can discuss at the end. So then you have another fully connected layer followed by a activation function. And this will be scaled such that you are passing it through the attention and you are getting the better attention feature as part of this squeeze and excitation. So what these students done is that, So the team from BTech Artificial Intelligence 2019 passed out in 2023. So they worked out, or they used, they modified this attention block and applied it to classify the chest X-ray images with the binary class. It's just a two-class classification problem. Because as they are undergrad students, they found it easy to understand about this data because it is a X-ray data. So it is the grayscale data, and moreover it is a data which is a standard one which was used across for years, benchmark data which was well labeled and annotated. Okay, and it was actually verified. So with this they have started with. So it has two class, one is normal, the other one is pneumonia. So how they have designed their methodology is that they have the deep CNN architectures, as I've already told. This comes as a backbone. So in that time itself, no, people would have heard about ensemble learning. So instead of relying on one DL network, the same will be passed through multiple DL networks so that you will be able to get the best features from all these things. So you're concatenating. Say, for example, if I want to keep an analogy for this, if we are going for any opinion, we'll not just rely on one person opinion, right? We will at least take 3 to 5 members and we'll try to get the best out of it, right? The same logic was applied here. And how do they get at these five? I'll tell it in the experimental design. Okay, so as of now they have five deep CNN architectures, which has been, the features are then passed to the concatenated features are then passed to the attention block. So what is the attention block here? They have the squeeze and excitation block. But since they are taking the features concatenated from the not just one standard convolution neural network, but the best performing convolution neural networks as an ensemble approach, they were able to reduce the number of intermediate layers with just one fully connected layer. They didn't go for no like two fully connected layers and the two activation functions. They just went for global average pooling with a one fully connected layer followed by an activation function. Okay, and this serves as the attention block. So this is one of the main contribution in this entire methodology. Okay, so this was passed through a dense network where no, we are going for the dimensionality reduced features. Why do we need a dimensionality reduced features here? Because we have taken the features from all the best networking models, right? So manually, or in order to analyze no which features are the very best from all these selections, you have to do a one level selection. So that is where no this kernel principal component analysis was applied in order to select the best features out of the ensembled features, after which it has been passed through an attention. So from the attention we have to select the best features. Okay, so that feature, those features were concatenated. So every thing we have to the best features based upon this dimensionality reduction after passing it through the attention. So that is the most important point. And then we have the ensemble. Now the question is, why can't we just have a softmax classifier here? Why do you go for the ensemble ML? You know that no, if the features are really very best, your ML can do a better task rather than your DL, right? So with that basic, or with that analogy in mind, so this logic was done. So this was passed through the stacking classifiers in order to classify it as a normal or pneumonia. Okay, so this one, how the experiment was designed is that you can see that all the almost no top 10 models were tried from the convolution neural network with the attention. So the corresponding attention block, right? So this attention block which we have proposed with just one fully connected layer instead of no multiple layers, unlike in the original contribution. Okay, so this was being first experimented. So this is how they worked as a semester wise. So in one of the semesters, they just saw the effect of attention in it, and they found that for all the architectures, it was able to improve the performance at least by 1 or 2 percentage. In certain cases, it was even able to improve about 3 to 4 percentage, all in terms of no precision, recall, even F1 score, and the area under the curve. People know that no, these are the standard metrics that is used for the performance of the to analyze the performance of the classification task. So each of this model, or all the models with convolution neural network, was able to do a better job when the attention was embedded in it. So after getting these results, they took the top 5 models, and that is how these models came in: DenseNet, ResNet version 50, 101, and 152, along with the exception. So, and then you can see that the data distribution was imbalanced. So we didn't take up this problem as a tackling it as a class imbalance problem. So what it was done is that because this data set already, the published works mentioned that they do a kind of data augmentations in order to go for no almost in order to avoid the class imbalance, so that you get almost the same number in while training it. Okay, and the validation is also same, and you have a different test numbers here. So these one will not affect your data much. Say for example, if you're rescaling it, sharing it, zooming it, flipping it, the information or the feature associated with your normal or pneumonia will not be affected much. So this was gathered from the literature, and the corresponding augmentations was done so that we reach or we avoid the class imbalance problem, and we have almost the same number of data for the normal and the pneumonia. Okay, and this is a validation train test and the validation split. So we were able to see that the features, after being subjected to the attention, and the best features are selected through the dimensionality reduction algorithm, we were able to see that the features were actually well separable. So this visualization was done using the TSNE plot. So this one helps us to project the high dimensional features to the lower dimensional using the principal component analysis. So this feature visualization plot shows that the okay, it was able to, the features are actually well separable. This is the reason we just went for using the machine learning classifiers itself instead of just going for the softmax here. Okay, so here you can see that there are very few validation data points that was actually overlaying. Else, in this one, we were trying to visualize it for all the best networks. So this is just one sample which has been shown. Okay, but this was shown for all the best combinations of it. So the details of all these plots and things are given in our publication, which is given at the bottom of the slide. So moving ahead, so this is the GradCam visualization, where you can see that no, the correctly classified. Okay, so pneumonia region. Okay, so the first one, the first row stands for normal, classified as normal. So in order to see here, you can see that in the normal, it was trying, there was no any infection in the lungs, so it was not giving, I mean, it was able to see the variation with respect to these two, right? If it is case of pneumonia, you can see that the affected regions. Okay, so this is a clear X-ray, this is a pneumonia affected. So in this case, we didn't have any annotation. Like annotation, when I see where the pneumonia is there, is not there. So what we did is that we just got the GradCam visualization map from the feature map, and we were able to see. But what we are able to infer is that at least when it comes to pneumonia, it is able to see some features within the lung region, whereas in normal, there is no much infection, right? So the transform is, this is what I was telling in answering one of the people question, like what is the difference between this reinforcement thing. When you see, no, here if you see, it is just trying to learn the difference between the data that has been given, right? So in this case, it is seeing that there is no much region that has been affected, so the dominance or the things are going towards the outer region, whereas here it is able to see within the lung area, and it is able to go for the thing. And one more thing I want to highlight, this is done for the this is done specifically with respect to the one particular standard data sets that was available for the pediatric pneumonia part. Okay, so this has been validated on this particular data set. So we were able to compare the accuracy with all the previous published works, and we were able to give good or the comparable accuracy with the attention module, and we were able to provide it with the visualization, telling that no kind of explainability was been involved to tell that what the network has really seen in order to tell that this is the normal X-ray or this is the pneumonia. And one thing what we did is that we validated this on a completely unseen data collected from a different environment and the different part. And there we could see that our model was able to, the trained model was able to do a decent classification score there. And we were really convinced with this, or we were really satisfied with the performance on the precision in normal. So when you see that the precision in normal is high, that means there is no false positives involved there, and there were only false negatives. False negatives, when we say the normal has been classified as pneumonia, but still there, if you see, no, you have the doctor's support there to go and again diagnose, or you can go and again check. If it is other way around, it is difficult, right? If it is pneumonia and if it says a normal, then we are missing a case. That should not happen. So that has not happened in our model. And similarly, pneumonia, if you see, the recall was good. So when you say that the recall was good, the false negatives were less. Okay, so that means false positives were there. That is, there were few pneumonia which was classified as the other way around, like normal. It was actually no telling that it is not a pneumonia, but it was classifying it as a pneumonia. But again, I'll tell you that even in this case, we have the after this is all been designed for the initial screening. So of course, you can have at least the lab technicians to go and validate at least these things. Okay, so it is a completely unseen model. It was able to do at least a decent job, not actually an very excellent performance. Okay, so just moving ahead. So this one was actually yeah, was published in the Q1 journal. It is an engineering applications of artificial intelligence. So this the team take over by just analyzing all the deep learning architectures alone was done in one semester with respect to the attention they were exploring it, and then experimenting no all kinds of the ablation studies. So what do you mean by, what is meant by the ablation is why we need only one excitation. I mean, why do we need only one fully connected layer in the excitation squeeze and excitation block, which is an attention block that has been proposed, motivated by the squeeze and excitation thing that has been proposed. So what if you have more than two, and what are the different variations of the parameters we took in terms of the hyperparameters? So all those detailed experiments are actually presented in this article. Okay. So now moving ahead towards this. So that is what we have seen is with respect to just a single head. So you don't have any multi-head attention coming there. So that work was done just with a single head attention. And moreover, the features that has been taken is from the backbone of the convolution neural networks. Okay. So now moving ahead or moving towards the vision transformer. Okay. So in the vision transformer, as I've already told, here multi-head self-attention plays an effective role, and that forms the most important contribution towards the vision transformers. So here, as you know, the transformers was actually, as I've already mentioned, it was actually borrowed, or it actually adopted from the natural language process community. So natural language processing, they pass the words, okay, or a sentence in which the multiple words you can see in a sequence. So how it is taken care in case of the images is that the image will be split into patches, and each of the patches is actually passed as a sequence to the transformer network, and the transformer network was able to learn the structure associated with it. As I mean the structure, it should be able to learn not only the features but also the orientation or the alignment of the features with respect to that of the original image which we pass through. So the this is the very first vision transformer, and one of the okay, benchmark the standard pictorial representation that goes left and right. Okay, so this is an image worth 16 by 16 words. Okay, so why that 16 by 16? It has actually been divided into 16 by 16 patches. Okay, that forms as an input to your transformer. Okay, so what is the step that actually comes in? You're not passing the image as a whole, unlike I mean image as a whole, unlike your CNN. In CNN, if people have already worked in, you know that there will be a small filter, or there will be a small receptive field in order to capture the local information or the local feature, and the same weight will be shared across all the images. So what I mean by the same weight, it gives equal attention to all these patches. Okay, so that is where in your CNN. Whereas in transformer, what are we trying to do is that we are trying to split as the patches, And remember that each of these patches has the positional embedding. So as I've already mentioned in my previous slides, one of the previous slides, so you can see that when you go for the positional embedding, you can recreate back the structure of the image. Say, for example, in this case, if I see the attention score for the fourth patch is high, I could go and look for the corresponding fourth patch here. So it has been embedded in the row wise. So it starts with 0, 1, 2, 3, 4. So I could see that the fourth patch has the most significant information, or in other means, it is trying to learn the local information in context with the global. So if it is suppose a top building in some place, so what are the local features that contributes towards a building, which region is really very important. Say for example, if I'm viewing a building and I could recognize that as no, like Taj Mahal, if I'm seeing a photo, if I'm could able to recognize that as a Taj Mahal, I have a structure, right? What it has been seen, like the tomb and the four pillars around it. Whereas the CNN will look for only these. It will not associate with the structure of it. Whereas the transformers, because of this positional embeddings, it will be able to associate with that structure. So what do you have? You have a linear projection of this. That linear projection of this. So what do you mean by flattened patches? Each of this patch is actually a matrix. You just vectorize it so that it becomes a flattened patches. So each of this patch has been given a positional and embedding. So it labels 0, 1, 2. So this total number of patches, and all the patches in this case has been, that is where no the difference in scale comes in. So here it is uniform scale. So what do you mean by the uniform scale? Each patch will be of the same spatial size. Say suppose this is 16 cross 16, each of this patch will be of 16 cross 16. Okay, all of the patches will be of the same fixed size. So this will be passed to the transformer encoder. So what do you have in your transformer encoder? Your embedded patches goes as an input. So of course you have the normalization here, similar to the batch normalization in your convolution neural network, which ensures that distribution follows your Gaussian distribution for the better learning. Okay, so the normalization process is there. And here you can see that you have the multiple single head self-attention coming into the picture, which goes as the multi-head attention, followed by a normalization. And this is your multi-layer perceptron, okay, or what you call it as a fully connected layer. So this transformer encoder is the one which plays a role here. And then you have the final head layer, which stands as an important component towards your classification. Okay, so you have a multi-layer perceptron head, which looks for the attention and the positional features into it. So this is, if you see, no, it is called as a pure transformer model. Why it is called as a pure transformer model is it is not relying on any convolutional operation here. It is completely dependent on your scaled dot product of the attention scores for your values, and it is not related with any of the convolution operation. So this is a completely pure vision transformer model. Hope that is clear. So this one, again from the same batch, this is another team who didn't take it up as their project, but just did as their term project out of the deep learning for signal image processing task. And here they worked for the satellite image classification. So these are the number of classes. So what is the knowledge we have is that usually these target classes, if you see, they are mostly associated with the land use and land cover. So what we mean by the land use and land cover in remote sensing is that you are dealing with the classes which has been covered in land. Say for example, it will be either related to the crop type or related to the forest area. So mostly it is buildings. So mostly it is, if you look, no, it is looking for a green and non-green region. So that is what, because no, this is actually a satellite image. So you'll be seeing it at a larger scale. So you'll be seeing it as the green and the non-green thing. And this, they are going to use it for the land use land cover classification map. So this is actually no used for making a town planning maps, all those things. So that is what the higher end of the application that actually comes in. So here they were given the multispectral bands. When you say multispectral bands, it is nothing but you have the visible region, that is your red, green, and blue. You have other regions in the electromagnetic spectrum which are actually covered under this satellite sensors as the images. So because of this target classes, what we analyzed is that since it is green and non-green, can we go ahead with just the visible region information and the visible region in near infrared region, because near infrared is theoretically it tells that no, it is one of the bands which differentiates between your green and non-green part. Okay, so in this we were trying to recommend that all the spectral bands may not be necessary for classes which you are dealing with your green and non-green. So that we were analyzing it with respect to the vision transformer. This went just as a conference level paper. So there is a very high scope for the improvement of this work. Say, for example, they worked with the pure transformers. What if the hybrid transformers, or what if no, you have the backbone of the convolution neural networks for all these things were actually unexplored in this work. So the scope of this work is very much limited to explore the attention mechanisms with the pure transformers with respect to the land use, land cover classifications with just the visible and the near infrared spectrum, which is affordable when compared to that of the multi-spectral bands as terms of the cost is concerned. Okay, so if you see that what we analyzed is that the vision transformer, the same vision transformer, the base vision transformer model, which only the parameters we changed it, and the parameters which we changed has been given here. The patch size, as I've already told, in the pure vision transformers, you have the fixed patch size. So all these patches are of the same size of 8 by 8. And the number of heads, I told you, right? The number of single head self attention is one of the hyperparameter that has to be fixed by the user. Here the ablation experiments were not done, or it was not, they just know they were trying to change it, the number of single head self attention maps with respect to their loss plot with the validation data. So the much of the ablation experiments has not been done here. So that is another scope of extension of this work, or one of the open gaps still exist. And the number of the transformer layers, so you have a transformer encoder layer. Each of the encoder layer is associated with your multi-head self-attention, followed by the fully connected layers, or your multi-layer perceptron, right? And you can define your number of encoder blocks, and the number of encoder blocks defined for this work was 8. And the data augmentation techniques, just to avoid the class imbalance problem, what all the data augmentation techniques that has been taken place has been given here. So what we analyzed is that if you see this, the vision transformers were able to learn better along with the near infrared region provided with the RGB. Say, for example, no, the few samples has been given here. So what is this few samples is all about is, you can see that those are actually dealing with the building area, as well as no certain things are with the crop area, the green areas, right? So in these cases, what we understood is that the attention maps, which are actually overlaid in the second row, if you visualize, or if you see this, the self attention maps through the transformers, the last layer. Okay, we use 4 encoder block, right? The last layer has been taken for this feature visualization. And what we observed is that rather than only the RGB bands, the RGB with NIR bands were able to give the most significant attention features with respect to the class, so that whichever has been misclassified, say for example, no, it was actually the right class is annual crop, but with only the RGB spectral band, we were able, or RGB band, it was misclassifying is into another class. But whereas with RGB plus NIR, it was rightly putting into the right class. Okay. So everywhere, even if you look for your area, this is actually a highway, but it was putting under residential, because there is no much of the buildings here, although there are very one or two which looks like a building. But when we gave the NIR along with the RGB patches, so this one, say for example, what attention it has learned, and I'm encoding back to my original image structure, I need the positional embedding, right? Then only I know which patch fits here. This is the reason why the positional embedding is very important at transformers. So this was able to give the correct classes along with the RGB NIR. So we were able to recommend that for which of the classes the RGB is required required and for which of the classes RGB and NAR is required. And in these kind of, if you're looking for designing, if you're looking for the sensors which should be able to data, which should give us an images for these kind of classes related with the green or non-green area, you can go with only the RGB and NAR bands. No need of the any other spectral bands was a kind of recommendation output from this work. So this was published in the International Conference on Frontier and Intelligent Computing. So this was finally published as one of the book chapters in Springer. Okay, so this was also an outcome of one of the BTech groups who did it as a term project and close their work. They didn't continue it as their BTech main project. Okay. So now moving towards the, so whatever we have seen now is actually the vision transformer, which comes under the multi-head self-attention under uniform scale. What is the multi-head self-attention? You have the multiple single-head self-attention. And what is meant by uniform scale is that each of the patches will not be of the different size. It is all of the uniform size. And remember that we don't have any convolution operation there. It was purely designed based upon your attention blocks, which is nothing but the scaled dot product of your attention scores to the values. So, and then you have the multi-layer perceptron. That's it has been involved there. But now you have the next type of transformers coming in, which is actually called as the hybrid transformers. So what we mean by the hybrid transformers is that we have the advantage of the convolution and the vision transformers coming in. So this is actually named as CVT, introducing convolutions to the vision transformers. And this is also from the same International Conference for the Computer Vision. This is not CVPR, this is CVF. So this is also the top ranked IEEE International Conference in the computer vision community. So what we have here in the vision transformers, they were going for the position encoding. Of course, it is required for your restructuring or structure back your original patches with respect to that of your original image. But in case of the convolution transformers, they didn't opt for the positional encodings. But this one, why? Because no, you can see that each of the patches which has been taken from the vision transformers. I'll just move that slide just a second. So if you see that, remember that these are called as the non-overlapping. So what do you mean by non-overlapping is that, so if you have taken this patch of size 16 cross 16, you will move to the next 16 cross 16. So you will not have an overlap between these patches. So whatever information in this patch will not be there in the next patch. Okay, so you don't have any common information between the patches. But here they are going for the overlapping patches. So overlapping patches, this they are using the convolution operation. So you have too many number of overlapping patches here. So unless otherwise, if you don't want to get the structure back, it is fine or it is recommended to go for your overlapping with the convolution operation. And then the projection for each of this attention maps, so far in the vision transformers, they tried only with a linear embedding, but here it was tried with a convolution embedding. And so you have a kind of the hierarchical transformers. So we'll just see this. What is this convolutional vision transformers, or how they have embedded the convolution layer along with the transformer layer. So this is one of the benchmark architectures working for images in computer vision. So what is the main properties of the vision transformers, or why do they need the positional embedding? Okay, so the positional embedding is for our reference in order to get the structure back. But whereas with respect to the transformer information, the important property there is it is permutation invariant. So what we mean by the permutation invariant is, as per the self-attention is considered, so this is a representation of an non-overlapping patches without the positional embedding. So if you see here, even if I pass this patches like this, say for example, no, this is not passed in an order. Okay, you can see that it has been passed randomly. So as for the transformers model is considered, or the network is considered, this left side positional embedded patches and the random patches look remains the same. Okay, so only for S, in order to retrieve back to the structure, we have that positional encodings. But as for the transformer point of view, this and this remains the same. It is just going to see as one of the patches in your past image, and it is going to compute your attention score. So say for example, in this, it may give the attention score as maximum for the last patch, but this last patch is not corresponding to the corresponding last patch in the original image. If I want to trace it like that, I should have a corresponding positional embedding. If I don't have a positional embedding, I'll be able to see the important attention map given by the transformer. But where should I relate it to my original image? It is very difficult to do that. Okay, so that is one of the properties lying, that is actually called as a permutation invariant in the vision transformer. In case of the convolution, what is the advantage you are going to have is that, or people call this as a hard inductive bias. What is this hard inductive bias is? There is actually a property of translation invariance associated with the convolution feature map. So what is this translation invariance in the convolution feature map? And what is this translation equivariance connected to the convolution operation is what we are going to see it here, because this is one of the important properties associated with CNN. If you want to attain this property in transformer, the number of images required for the transformer is needed is still more larger, or it requires large number of images than what is required for CNN. Okay, so CNN will be able to learn, say with 1000 images, the transformers require more than 1000 in order to achieve this property. And this is called as the hard inductive bias. What is this is, you can see that this image, even if it is slightly rotated, or if it is in a different position, both belongs to the same class. Okay, so this is one of the important properties that the network should capture, and this is the one which is captured by the convolution operation. So if you map it to the feature map region, both this should represent in the same point. So this is what we call it as the translational invariance. So how are we achieving it? This is not achieved directly by the convolution operation, but you have an operation called max pooling followed by a convolution. Say for example, you have a 3 by 3 matrix. Okay, so this 3 by 3 matrix, even if you translate it and take the maximum value, your maximum value is not going to change. It is going to be the same. Okay, so this one convolution followed by a max pooling, that operation together embeds this translation invariance property, which is actually required in order to have one of the properties which we require in order to have the best classification performance. And what do you mean by equivariance is that if you apply the convolution operation on an original image, or and then you translate it, it must be same as translating the image and then applying the convolution operation. Okay, so please get that point. Okay, so what you're doing, you're doing a convolution operation on the translated image. The other one, what you're doing the convolution operation on an image and then translating. Okay, both should be the same. So this is what is actually called as the translational equivariance, and this is been achieved in a convolution operation. And these properties, we call it as the hard inductive bias. So this is the advantage in your convolution neural network, which is not possible, or which is possible in transformers only if we have large number of images than what is required for the CNN. So what they have done here is that, so this particular paper, okay, so this is the paper, no, where they have mentioned as COTNET. What is that? COTNET is convolution plus attention. Okay, so this forms the basis for your convolution vision transformers, or in other means, it is called as the hybrid vision transformers. So you have your convolution plus the transformer there. So this is why it is called as the hybrid. And this is actually marrying convolution and attention for all data sizes. So why all data sizes? I'll come into picture. So far, we have discussed only about the uniform size. So what do you mean by the uniform size? You're going to have the all the patches are of the same size. So in this, what we have, translation equivariance property is well captured in your convolution, whereas input adaptive weighting. What is that input adaptive weighting? Each of the patches will get a different attention scores, unlike the CNN. CNN is going to share the same weights. Okay, so it is going to have the same weights throughout all the patches it looks for, whereas self-attention is going to give you the weighted score for all these patches. And moreover, it is trying to capture the global receptive field by giving the weightage to the local patches, which is not possible or which is not there in your convolution operation. So combining these two is what the transformer came, which is called as the hybrid vision transformers. So now we have moved from so first what we have seen is the important components under the vision transformers. And then we have seen what is the advantage or what is the important properties in convolution. So the next, it has passed to an hybrid, which is nothing but the mixture of the convolution and the transformers. So one of our publications, what we did is that we didn't go for a pure transformer model. We just went for the single head self attention as the backbone to the CNN. That is what our contribution in our X-ray classification, X-ray image classifications for the binary classes. So in this, yeah, if you just see, what we have is that we are going for an overlapping patches. So in this case, your input is not going to be a non-overlapping. You're going for an overlapping patches. And these overlapping patches are passed through the convolution operation. So if you just map it to your vision transformer, you can see that, just a second, if you go for this vision transformer, what we have non-linear, non-overlapping patches, and you have a linear projection. Whereas here, what you are going to have is that when you say linear projection, you just have your matrix. Okay, you just do your dot product. Okay, or you do your what is called as a project. That is what is actually called as a linear projection. Operation wise, what you're doing is your dot product. Okay, matrix multiplication over the vector is what you're going to do. So here, what you have is, instead of the linear operation, you're going to have the convolution operation. So this convolution feature maps goes as an input to your convolution transformer block. Okay. So in this transformer block, you can see that what you have, you're just passing the convolution projected feature maps, not the linear projected batches. Okay. So that is not your input. So what you are passing is your convolutional feature maps as an input. And moreover, the feature maps, what you got is with the overlapping patches. And the rest of the heads remains the same. So you have the same multi-head attention followed by a normalization followed by a multi-layer perceptron. Okay, so those features remains the same. So this serves as your attention maps or the token maps. And this is passed through the, as we see, there are actually number of transformer encoder blocks. Similarly, you have the number of convolutional transformer blocks in case of your convolution vision transformers, or in other means, which is called as the hybrid vision transformers. Whereas this all remains the same as part of your pure vision transformers. So you have your multi-layer perceptron head, and of course you have your softmax as your classifier finally to decide your classification part. Okay. So now moving ahead. So what we have here is that, so this, of course, no, all the vision transformers, if you go through that survey paper, which I have mentioned in the taxonomy of the self-attention. So that survey paper, they have covered right from no all image processing task which we do. Okay. Right from the classification to the object detection to the segmentation. Okay. And many things in videos, 3D, everything they have covered. So since it's just a 2-hour session, we'll not be able to cover a lot. Okay. But I'll be able to give the theory behind all these things, which will help you, if you've understood, which will help you to read through those applications. Okay. So one thing or one of the benchmarks which includes the hybrid transformers or the convolutional vision transformers is actually called as the detection transformer. So they were able to extend this for an object detection problem. And this one, they call it as, no, or they see it as the advantage over what you have it in your conventional convolutional based object detection. If people have worked with the convolution based object detection, one of the benchmark algorithms there is actually faster RCNN, which looks for non-max suppression operation, which we call as NMS, non-max suppression operation. That is nothing but, no, you get more than 3 bounding boxes over an object. You just select an object which has a maximum overlap with that of the ground truth, or maximum coverage of your object. What you have, you just have that. So in this, they've completely avoided that non-max suppression operation, and they were able to bring it as the object final object detection part. How are they able to do it is that they have four modules here in their network. One is the backbone module, that is nothing but you have your overlapping features, you have your convolution neural network in order to extract the features. Then it is followed by encoder block, decoder blocks, and the prediction heads. So remember that this encoder and the decoder blocks are the transformer based. So what we have seen in the previous with respect to your multi-head self-attention, multi-layer perceptrons, all those comes here. But what is the difference here? Instead of having it as your linear projection of the non-overlapping patches, you will be having your convolution feature maps as an input towards this. And in the prediction heads, the thing is that it will not only, it is of course moving through your multi-layer perceptron or the feed-forward network or the fully connected layer. All these means one and the same, used by the different terms. So here, it not only learns about the object class, it also learns about the no object region. Okay, so it avoids all the blocks with no object and it just gives the output for the box which contains the class. How are they able to do this? Okay, because we already mentioned that transformers works for the self-supervised, which is actually learning from the lot of unlabeled data rather than relying on the labeled data. Labeled data, finally, it is fine-tuning it, right? So how are they able to do this? Here comes the one of the important laws, which is actually called as the bipartite matching laws. Okay, so how do they do that? Is they are trying to associate the bounding box with respect to the object as well as for the no object. Okay, so how are they having this is that this matching they are trying to get it with the most less number of steps. Okay, so that is the most important part that lies in this bipartite matching loss. So of course you have your CNN features, you have your transformer as your encoder and the decoder, but what are we trying to look at is that can we have the best match between the boxes that contains the objects rather than the no object. Okay, but while learning, no, the transformer is because why it is able to learn even the box without an object. That is because it is able to see the patches of the images. What those patches are nothing but the features that has been given as an input from the convolution. So it is something like no, you are getting the training directly under a top person. Okay, a person, say suppose you are in a research community and there is a person who is top, so that why we call him as a top, he has all well knowledge in that. And say suppose you are directly working under him rather than no, like a third level when we say there are two intermediate persons between them and you are learning under him, right? So in that case it is actually a pass, but whereas when you are learning directly under, you are able to grab more, right? So similar to that, what they have is that they have a bipartite matching loss, which makes the network to learn well about the object class and then just leave the non-object class, no object class, without using the non-max suppression operation. Okay, so this you have a okay, very large number of steps in this, because this algorithm itself, no, we can discuss it for another 1 hour. So you have that many to discuss in this law. It comes under no exploring the loss functions. Okay, so if we have a session on complete loss functions alone, this can be covered in detail there. Okay, so this is the loss function that has played an important role in the detection transformer. So here the hybrid convolutional transformers from the classification has been extended towards the detection task. Okay, so this was the title of that paper, end-to-end object detection with transformers. So this is presented in the top conference, which is nothing but the European Conference on Computer Vision, ECCV 2020. Okay, so if you see here, this is the output what they're able to get from the encoder block. Okay, because decoder tries to map this towards the class detection problem. So what are the features it is able to see? You can see that no, the because of this patches and because of this attention scores, it is able to see the individual objects very well apart from your background, or what we call it as a no object region. And this plays an important role for a saliency detection application also, which plays plays a base task for your image retrieval. Okay, so here you can see, the self attention, what they're able to capture. So here, though there is no positional encoding, they were able to map it. This is because now GradCam visualization, you will be able to see the attention scores, so that you are able to map it to your original image. So you'll be able to say roughly, it will not be an exact patch match, but roughly you will be able to see which object it is. Okay, so this is one of the intermediate results they have shown in order to show that why then a network is able to see the significant object features leaving the background information. So here there are three main objects, and of course there is some object okay, a part of the cow's face, slightly visible, but even that it is able to capture it. Some object is there. Okay, it is well visible. Whereas this may not that visible when you go for just a uniform weight based upon the convolution neural network operation. So all these attention scores shows that. So this is taken from the encoder block. The same paper, the output has been shown. Okay. So next, so still now, just to summarize, what we have done is we have done with the multi-head self-attention vision transformers, which have been covered under the uniform scale, and the hybrid. Hybrid is nothing but which takes the advantage of both the convolution and the transformer. So instead of linear projection, you will be passing the convolution feature map as your input to your transformer instead of the linear projection. So till that we have covered. The other one of the benchmarks in the transformers, which is actually a multi-scale vision transformer, is called as a swin transformer. So what is that swin? Is nothing but shifted window. That is what is actually called as swin. S stands for shifted, WIN stands for window. This is where it is called as a swin transformer model. So this was published as an hierarchical vision transformer in 2021. It is in the ICCD conference, International Conference for the Computer Vision, by Liu Zhu et al. So here, what you have in the right side, if you see that, what you have in your vision transformers, you're going for only the uniform scale. So uniform scale, if you see, this is just 4 by 4 patches, or each of the patches of size 16 by 16. So you have the fixed spatial size for all the patches. And what we have seen there, we went for the non-overlapping, and using convolution, we were able to go for the overlapping. But even in convolution, even if you go for overlapping, each of this is actually a fixed size. Unlike, there is actually one of the layer which you can include in convolution neural network, which is called as the spatial pyramid pooling layer, SPP layer. If you include that, then it is possible to learn for the multiple different regions. Okay. So this idea has been borrowed from the conventional image processing, which is called as the image pyramids. So what do we mean by the image pyramid is that I hope people are well able to visualize your pyramid structure, right? So what we have in the pyramid structure, you are able to see your image under different scales. Okay, so it is actually, people say that slicing. You are slicing under different resolution and then seeing it. So if you see here, what you are seeing at the top is each of these patches is of 16 by 16. So you have less number of patches because each of the spatial size is high. So you will get only the less number of patches there. But when that each of the patch size 16 by 16, if you are reducing it to 8 by 8, you can see that the number of patches increases. So what do? You are trying to see more localized information by reducing the patch size. So as the patch size get reduced, the number of patches increases. So this is the simple logic which we can easily visualize. So what are we going to achieve here? We are able to see the image informations or represents the image informations at different scales. Okay, that is the difference from the uniform scale vision transformer. So this is called as the multi-scale vision transformer. So what we are doing, we are looking at the different spatial size. So as your spatial size varies, your number of patches also varies to as an input to your transformer blocks. So this forms the very basic part, or that forms the difference in your swing transformers, shifted window transformer. So this comes under the multi-scale vision transformer. So again, I'm repeating, what we saw in the pure vision transformer is a uniform scale. And what we have here is actually the multi-scale. So how are we able to achieve this is, This is why it is called as a hierarchical vision transformer. So each layer by layer, you'll be dealing it with a different spatial size. Say, suppose if you have a layer L, so the number of blocks here is 2 by 2. So 2 by 2 means there are only 4 blocks. So in this 4 blocks, each of the total patch size, if you see, the total patches, if you see, it is of the large size. In layer L plus 1, you are going to increase your number of patches. So in this case, it is 3 by 3. And you can see that each of the patches are of different size. Okay. Say, for example, the first patch is 2 by 2. This patch is 2 by 4. This patch is 2 by 2. This patch is, or this window, sorry, I should not call it as a window. So patch, it is actually called as a window. Again, I'm correcting myself. So this one, which is in that maroon border or the dark brown border, we call it as a window, inside which we see it as a patch. Okay. So this particular window, if you see, it consists of the 4 by 2 patch. And this window, if you see, it is a 4 by 4 patch. So every layer, it is trying to learn about. So this one, how do we define it? Okay. So this goes for the random thing, but only thing what we have to ensure that the number of patches is actually increased. Okay. As you go from layer 1 to layer L plus 1. So as the number of patches increases, a number of windows in each of the layer increases, your number of patches, okay, it's actually increased with the less spatial size. So if the spatial size, no, if you're looking at a 4 by 4, this one you're going to look it at a 2 by 2 scale. Okay, so this is what is actually called as the shifted window transformer. So how they form a block is that as you go for the multiple transformer encoder blocks, or as you have the multiple convolutional transformer blocks, what you have here is the multi-scale shifted window transformers as the different blocks. So what you have here, we'll see the architecture this. So what do you have? You have your patch partition. Your patch partition is either you can go for non-overlapping, or you can go for overlapping using the convolutional feature maps, or you can go for the linear embedding. And what you have in the spin transformer block is that you can see that the right hand side where my laser pointer has been pointed, these two together form your spin transformer blocks. So what you have here, of course, you have your layer normalization, you have your multi-layer perceptron. All these are actually same as your transformer blocks. But what makes a difference is that what you have here is the multi-self attention for us every window. That is what your transformer is doing. In addition to that, okay, in addition to that, so you have a connection between these two blocks. So in addition to that, you're going to have a shifted window multi-scale attention, multi-self-head attention. Sorry, it is shifted window multi-self-head attention. So what do you have here? All these transformers were working on the uniform scale so far, but whereas here it is going to work for the shifted window multi-head self-attention, and you have a connection between these two blocks. And this forms the one swing transformer block. So as you go from, any doubts? May I request to mute yourself? Okay, fine.
Participant, mute your mic.
Fine.
Yeah,
So as you
wait, ma'am.
go, as
I
you
will
go
check.
for,
Yeah.
yeah, as you go for different stages, you can see that your height and width is divided by the particular window size, right? So if I go for 4 by 4, you will have the large patches as you go. But as you go on increasing this, your patches goes on decreasing. So as you go on increase your resolution. Say, for example, if you're moving from 4 by 4 window to 8 by 8 window, your patch size will be reducing there. So 8 by 8 to 16 by 16, your patch size will be reducing there, but you will be able to get the more number of patches there. So that is how the different stages are being designed in your spin transformer block. So here you have multi-scale, which is actually borrowed from your pyramid image pyramids. Okay, so that is looking at your image at a different resolution. Okay, so this one, yes. Now coming to how the self-supervised part, or how the transformers is able to learn from that approach. Okay, so this is where no, it is different, of how it is different from reinforcement I was trying to explain. So this is what is actually called as the contrastive self-supervised learning. So a very good illustrative example has been given. So I have just acknowledged that block in the blog in the bottom of this slide. So if you see this, the contrastive self-supervised is the left hand side, whatever has been drawn is a person is asked to draw okay, a $1 rupee based on whatever he has seen. Okay, the other one he was asked to draw by exactly seeing that. Okay, so you just try to understand the difference. Okay, by exactly seeing, I'll be able to reproduce each and every portion in that image, right? In the left side, when I asked to draw, what immediately comes to my mind is the most significant or the important features that actually makes it different from the Indian rupee. Say for example, Indian rupee, if I have Indian rupee in my hand, I'll draw exactly of what I'm seeing. But if I ask to draw without seeing, the first and the foremost what comes into my mind is the respectable Mahatma Gandhi, father of a nation picture, which I'll try to draw first. Okay, and then you have our nation's representation thing, so that you can see that those emblems or those symbols or those features are actually that comes into our mind, rather than no each and minute feature that is associated with that particular image. Okay, so this is what is actually called as the contrastive. Why it is contrastive? You, instead of learning all the features, try to learn the significant features which is actually required for an any object. So this is what we are trying to enforce in the self-supervised learning. So how are we, so this is the logic behind it, but how are we enforcing this? Because how do we, without a loss function, you cannot define this, because for you, I'll be able to explain. But the same thing, if I want to tell to my AI algorithm or a DL network, I have to represent it in terms of the loss function. This is one of the very important reasons, no, our head dean of School of AI always enforces that the mathematics is really very important for no, in order to go for a larger scale. Okay, say for example, no, if I'm looking for shining in the area of AI for a long term, okay, sir always emphasize that you must have a very strong role mathematics. Okay, so you must be able to modify your loss functions accordingly, and that makes a significant contributions, rather than no, just as what I even we showed as the previous publications. We have introduced the block, but we didn't change any of the loss functions over there. Okay, so this comes under the significant contributions part. So how do these contrastive methods work is that, see, you have an object, all the augmentation techniques. What do you mean by the augmentation is that the translation and any of the patch. Say for example, if it is a dog, even the tail portion of the dog should be the part of that object, right? So all those we call it as the positive samples to an anchor. When we say anchor, the main object, so whatever portion that has been associated. Okay, I think people well know the okay description of an elephant given by the blind people, right? Because they'll just see one portion, they start describing, they'll not be able to connect everything, right? But whereas when we see, we were able to connect it with the structure. So here, when you see the score, what we want is that the object with all its aligned thing. When we say aligned, you can connect it with the data augmentation techniques like flipping, rotating, changing, scaling. Whatever you do, all those associated thing, it must be able to put it under one cluster. All the things that are different, say for example, if I'm looking for a background which is not related to the object anymore, that the difference between these two should be very high. So what are we trying to make is that the network should put all the similar patches into one group, and it should have the score for those as very high. Okay, so that is why it is called as the contrastive. Okay, so you must be able to well separate, or the score for those things should be very high, rather than the object associated with a negative sample. So remember that the positive samples are nothing but their own aligned part, and the negative is nothing but all which are not related to this. So this is how we are trying to make it, or we are trying to learn it. Okay, this is the contrastive method approach. So positive sample, it's very similar to the data point or associated with your object. Negative is highly dissimilar or away for it. So the score function is going to measure the similarity. So if the two is very close, the similarity score should be very high. And if the two is not similar, the similarity score should be very less, and it should be the difference between the similarity score should be very high. So that is what the loss functions thing we are giving in. So how we are able to have this is what, no, one more level of description is given in the deep info max. So what they were trying to do is that they split it as a global feature map and the local feature map. So all the local features should align with the global feature if it is the part of the subject. If it is not a part of that object, all the global feature with respect to the local feature should give a minimum score. Say, for example, if we want this dog as an object, so whatever you take it as a local information with respect to the dog should come as the high score. Whereas here it is a cheetah, right? So no longer associated with the dog. So this local feature with respect to this global feature should have a low score. Okay, so this is how the feature mapping or thing is there. So here you see they are not going to annotate things, but what are the augmentation things that comes under will be put under one group, and all other things will be under the different groups. So we have to create the as many number of positive samples and as many number of the negative samples. Okay, so that is where, so that has been captured through the global local features. And also you can see that how the invariance is learned. Okay, so one way of learning is that people, as I already told, you have an original image, you have the translated version, you have the blurred version, you have the light condition being changed, you have the object being placed at different places. Okay, so all those are actually passed so that it telling that all belongs to one class. So all these variations it should learn. The other one, if you see, people are able to give this the different representations. How are these different representations are arriving? This is through the basic image processing, or one of the most important area in the image processing is color image processing. Okay, so one of my areas, I mean the PhD, my significant role was analyzing these color image. Okay, the components of the color image analysis connecting to the convolution neural network algorithm was my important contribution or significant contributions in my PhD thesis. So if you see here, the luminance information will try to capture the most significant feature as an outline of an object, whereas the chrominance will be able to align the object based upon its color information. Okay, so all these things can be passed so that the network must be able to learn that all the based on these multiple information. Say for example, no, how we usually learn? Mostly we read, we listen, we see, we watch. Okay, so it is something like you are using your multiple senses in order to understand this. Okay, the same thing has been given to your AI algorithms now. So the contrastive learning, how do you create your invariances and how do you make your network to understand that it is the same? So from the same image, you are trying to create the variations through your different augmentation techniques or through the different representations of it, for which, no, all your basic image processing algorithms plays an important role. See, whatever we do it with the histogram equalization and whatever we do it with the contrastive enhancement, all these things forms the base for it. And whatever this, no, whatever we do it with respect to the color image spaces or the color spaces in images. Okay, so those all things. So we tell that all these are the same representation for the images belonging to the same class. Different class, it should make the difference to be very high, or the similarity score should be very low. So this one is the one which has been used under self-supervised transformers. So this is, I think most of you would have watched this. It is Dino from Facebook. It is distillation with no labels. Okay, so this is presented in ICCV 2021, and it has an excellent segmentation task in tracking. Okay, it is used in tracking in the live videos. Okay, it was able to do a wonderful job. Say for example, no, this is tracking the monkey with almost the entire object that has been covered. Okay, so this is actually based upon the self-supervised learning. So I would like to touch one more level high in that. So which, no, I think people would have heard in other terms, it is called as a student teacher model. Okay, so I take this example with respect to our own AI students. Okay, so they learn from us, but the way they reach in and the way they explore after that is actually, more in alignment of what we really taught them. Okay, so that is a exploration especially the younger community does when they want to really crack any higher studies outside those things. No, they are trying to learn more apart from what is actually aligned with the syllabus alone. Although there are much to learn from the syllabus itself in under AI designed by Professor Soman, but the other thing is they're moving okay, apart from their comfort zone in the early semesters itself. So in the student teacher model, if you see, teacher always has a global aspect, okay, and we must be able to make the student to reach that. How are they doing that? Is that the global information of the image will be always available to the teacher, but for the student only the most important feature of the object will be given. And the finally, of course, you have the transformers, everything, encoder layers, everything there. But finally it tries to match the softmax score of what the teacher has and what the student has. The teacher is looking and rating based upon the global. So in local, whatever, whichever thing, say for example, in this they are looking for just 3 class problem, in which, no, based on this the student core is giving okay, high for this, but whereas here the teacher has given high for the second, right? So until the student reaches here, so you can see that the training or the student will be correcting it based upon the feedback from the teacher. Okay, so this is what is actually called as a student teacher model. And finally what we are checking is actually the probability scores that comes out as a softmax probability between these two. So we are able to do it based upon the categorical loss. Okay, so this is a loss function which we want this to be minimum, where you can see that it is minus p2 log p1. P2 comes from the teacher model, P1 comes from the student model. So with respect to the teacher model, the student should able to attain that performance so that the loss becomes low. So how are they doing it? You can see that it is the same image. It x1 x2 says that as a two different representation. The teacher always has the global representation of the picture, whereas the student has the local. So when you say global, local, global in the sense along with the more background, the teacher will have the better knowledge. The student will be seeing the most significant features of that object alone first. Okay, say for example, no, if you want to drive this 2019 batch students towards the area of biomedical, first they have to learn about the basics of image processing, then basics of deep learning, then they must know the basics of research, how to do it, how, what's the literature survey, how they find the open gap, okay, how they find the research gap, how they identify the objectives. Okay, so it is actually, you can see that the teacher who is guiding or the team of okay, AI faculty members who are guiding always has the global picture, and this has been passed as the local, and they are trying to move. So of course that will not happen in a single semester, never ever. And the strong basics will be built by Professor Soman and team in the early semesters. Okay, so it is actually stepping over the semesters and reaching there. So similar logic comes here. So your student model, teacher, of course in every campus of Amrita follows the same. So you have your student model, teacher model. In the teacher model, you have something called as the centering. That is nothing but over the mean centered, because you can't expect the exact value. So you just have it as a mean centered. So plus or minus sigma value over the mean, you allow that better score for your student. Okay, but of course, no, we expect always very high, right? So although they don't reach, but if they're trying to reach and they reach there, you score it. So that is the reason why you have a centering, mean centering operation for the teacher, but you don't have that for the student. And you have what is the SG. Softmax, of course, you have, because these both are the one which you're going to compare. And what is this SG is top gradient. That is, you don't have the gradient flow in your teacher model, whereas you have that for your student model. Okay, because the student is going to update or upgrade or going to learn through the iterations based upon the feedback or based upon the thing given by the teacher. So you don't have the gradient flow or the back propagation. Okay, what we see it as an update or the weight update or learning in all DL algorithms. You don't have it for the teacher model, but you have it for the student model. Okay, so this is just I'm touching in for the thing which comes under the self-supervised model, or one of the benchmarks released by Facebook. Okay, you can just go and have. Okay, they have their live demo for it. Okay, dyno distillation with no labels. Of course, there is wide depth to go on to only into this approach. Okay, so that many of this is just an overview I have given. So how do they update, what all the things? Okay, so depth of it can be covered under the self-supervised approach itself, in which contrastive learning is just one of the methods or one of the approaches that has been highlighted here. Okay, so now what we have seen now is all related with, so far what I've talked is with dealing with the images, right? I've told that this has been borrowed from the natural language processing team and it was used for the images. But now the next, or it has already been started, I can say, people are looking for something called, as I've already told, it's a multi-model approach. Like how do we do, right? Certain things we write and learn, certain things we watch and learn, certain things we listen and learn. So here now the thing is that, or the research which has been started or happening for the last 2 years, if you see, or last 1 2 year active, you see, it is a multi-stream transformers. What is meant by the multi-stream transformers is that you give your image along with your text and speech, or because these are the three important modality of the data. So in this they've concentrated on the image as well as the text, but there are transformers which looks for the image, text and speech or audio. Okay, so all those aspects they look for. So this one is the multimodal learning. This, why we call it, there is actually a single stream transformers, multi-stream transformers. So multi-stream transformers, when you say, this is one of the benchmark architecture which is called as a visual BERT. As I already told, BERT is from the language model perspective. Visual part is, that's for VI. Okay, so this is VI visual BERT. So here you see you have your transformer separately trained for your language, and you have the relationship with respect to your images. And then it is learning what the cross modality is, that the self attention map from the language will be passed to the images and the image will be passed to the language. In the forthcoming slide I'll explain how it is. So this one, let's understand that why it is called as a multi-stream. Of course it works for the multi-model, but each of the model has been learned by the individual transformers. So how do you align this, or how do they use is that, see, for example, if you have a sentence, this is actually called as a tokens. Generally, they use a term called tokens related to either image patches or the language. Okay, each of the each of the word in a sentence, they call it as a tokens. Though I'm novice in NLP, but I've just heard went for certain terms. And of course, we have good collaborators in our own centers from who are working on the natural language processing. So for the last 1 year, we have just initiated by working, people with different expertise like image, speech, language have formed a team and we are working together now. Maybe within a year we are expecting a good outcome of it. So in this, if you see, humans learn language by listening, speaking, right? So here it is not just a sentence. For humans, you have a corresponding image. Learn, you have a corresponding image. The image that describes that word, okay, or the image that represents that word. Language, you have that thing that has been given by, okay, by all these by and all. It's very difficult to represent in terms of an images. Okay, so you don't have that, but how they just try to map with something, right? Listen. Okay, so you have, so there are certain things, right? If you have only the image patch, you guess the word. Okay, so we are trying to give the transformers that kind of learning. Okay, so this is one kind of approach which has been adopted to get the visually supervised language models, which is called as the, which has termed as a tokens. And this was used, and this is what I call it as cross modality. So how do they do the cross modality? For human, you will get the corresponding image token, and for the corresponding image token, you will have the, corresponding image patch token, you have the corresponding language word token coming in. Okay, so this is one of the approach that is used for multi-stream transformers. So this is an archive paper, which is called as the tokenization. Okay, so improving language understanding with contextualized visual grounded supervision. Yeah. So next, I'm almost about to finish. I just have this single stream transformer, and this would be the last slide, which talks about what is the most important activation function that has been used other than what is unlike in your convolution neural network. Okay, so in single stream transformers, also that also works for your multimodal representations, that is, which takes into image, language, and image, text and speech or audio. So here if you see, instead of having the individual transformers for each of these cases, it looks for the same transformer having all these as an input. So in this case, we must be very clear in giving their embeddings. Okay, how do you represent and how do you fix the feature length length is all important. It is not the individual transformers. It is the same transformer looking for all these. So the representation or the embeddings of it should be very clear here. Okay. This is the one which follows in the single stream, but mostly people are using the multi-stream transformers, and then you use the cross modality approach to have the better part. And the last thing which I would like to touch upon is the activation function, which is most commonly used in transformers. You would have heard of ReLU, a rectified linear unit, in case of the convolution neural networks. Whereas here, what you have is the Gaussian error linear unit. So as you can just see, so this is shown for the normal distribution where mean is 0 and sigma is 1. So you can see that in case of your ReLU or rectified linear unit, which is shown in orange color here, you have the discriminant value, right? Whenever the score is negative, it will be 0. Whenever the score is positive, it is just going to take the same value. That is where max of 0 comma x comes in. Whereas this one, which is called as a Gaussian error linear unit, it is actually learning the, it is given based on the standard Gaussian cumulative distribution function. So what it is trying to do is that it is trying to get the values, or it is trying to give the scores based upon the weights rather than just the sign. Because in a rectified linear unit, it just looks whether it is negative less than 0 or whether it is positive greater than 0. It is not trying to embed the value of the neuron as such. Okay. Whereas this, it is able to, although for the lower negatives, it will ignore the neurons because it is almost equal to 0. And also for the higher positives also, it almost takes as in case of how the ReLU acts or how the exponential linear unit acts. But in between this, okay, what you have is an important learning curve, which ensures that there is no vanishing. When you say vanishing gradient, your algorithm stops learning there. So you don't have an update of the weights over there. So that is actually taken care only by the activation function. That is the reason ReLU was most commonly used than the sigmoid function. Because if you know sigmoid function, 1 by 1 plus e power minus x, you know that it takes a S-shaped curve. So even if it reaches the little higher positive, it gets saturated. Okay, so you don't have any gradient flowing there, or it will not have any weight update over there. Similarly, for the all negative values also, it is so. Okay, so that is the reason people were appreciating this, or the vanishing gradient problem has been avoided by using the ReLU activation function or the rectified linear unit. Whereas here, it was able to still incorporate not just by using the sign function, but also using your weight values itself. So that is where your Gaussian error linear unit. This is the most commonly used activation function in terms of the transformers. Okay. So with this, I would like to end my session. So what I have covered so far is the basics of what is required to understand the transformers and what are the difference. So mainly just to touch upon, okay, it's the mainly this taxonomy, what has been covered with at least one network. So under uniform scale, we have seen vision transformer. Under multi-scale, we have seen spin transformer. Under hybrid, we have seen the convolution vision transformer. And under self-supervised, I've just touched upon with respect to the distillation part. Okay. So now I'm open to the questions. And any questions or
Participants, please
anything?
write your queries in the chat box, or otherwise
Yeah,
you can unmute and ask here. There is one question, ma'am. Wait, I will.
yeah, sure.
Yeah, it's regarding what is the effect of high stride on feature mapping.
Okay. So the effect of high stride is because when you go for high stride, you're overlapping, right? So what happens is that you're we are going for overlapping patches. So if you go for high stride, you will miss that overlap. So it becomes almost as a non-overlapping. So I'll tell that for non-overlapping, I can say that your stride is there is no it was actually the stride is 0. Okay, so you don't have, if I say stride as 2, between these two pixels, you have the between two blocks which you move, you have 2 pixels as common. So that is what you call it as a stride. So when you have a higher stride, the issue is that well, you have maximum overlap also there. So the maximum overlap, the disadvantage is that it is almost seeing every pixel. So it is not necessary to see every pixel because neighboring pixels will almost have the same information. So it is better to have it with respect to that of the larger, I mean, with the minimum stride, it will be better to have the patches. Is that clear? To go for multimodal problem as a beginner, would you suggest that? Pooja, do you mean that as a beginner, can we directly go for a multimodal? Okay. Yeah, only thing is that what you have to understand is that at least the domain which you are going to work in. Okay, so you have to understand about the data perspective very well. Okay, so it will be good no if you have a guidance from the faculty or from the whomever you call supervisors. No, it is not possible for a single supervisor to have all the modality to be in. So it will be better if you have multiple supervisors or multiple people who knows about these things individually very well, right? So in that case, it will be so helpful to you. But as a beginner, of course, you can go for multimodal problem. And I'll tell you, no, one of the most challenge what you will have is that the data set itself you may have to prepare from the scratch. Sometimes it is not no. Say for example, it is general computer vision problem. You may get it. Let me say that I have to work for a biomedical problem. What I've done, what we have done, it's not I. We what we have done is actually no pediatric pneumonia diagnosis, right? Using chest X-ray. Say for example, if I want to embed the report also along with this X-ray and the corresponding report. I'm really doubtful whether you will get such an data available as an open source. Okay, so if you're looking for a particular domain, of course it is good. Then you have to start from working on the data set itself will be a good contribution towards it. That is what the suggestion for it. Hope that's clear. If not, you can just feel free to ask more.
Is there any other questions from the audience
Yeah, Pooja,
regarding
thank
this
you.
session? Can write in the chat box.
So I'll just stop share my screen. So if you have
Yeah,
any specific slide, I'll get. If not, I'll just yeah.
yeah. There is one question, ma'am, from Pooja again.
Ah,
Any?